metallic chemists might be able to understand some of that. And then it was discovered that there was carbon monoxide and cyanide in these active sites. And so the first molecule that was so important to me, Don helped me find actually, is just the piano stool CP iron carbonyl dicyanide. And we showed that that was a direct mimic of the, or gave a direct mimic of the infrared spectrum of the active site of nickel iron hydrogenase. And from that, I mean, that was very exciting when we saw that spectrum. It just overlapped completely with the enzyme. And, you know, I figured out chemistry is chemistry. It doesn't matter if it's in the middle of an enzyme or in an infrared cell of a compound that we've made. Then my nickel into S2 chemistry came together with iron chemistry. I used metallo ligands, the nickel into S2 as a metalloligand to bind to iron tetracarbonyl. And all of a sudden, the hydrogenase spectroscopists were calling me and inviting me to meetings and inviting me to give lectures on these organometallics. And I have to say that that community was very welcoming to me. And all this time was so exciting because it was totally new. And I was so happy to be able to contribute my knowledge to that. So then in the final molecule that is so important to me came from the di-iron hexacarbonyl precursor to the iron active site in di-iron hydrogenases. By that time, my able competitor, Tom Rauchfuss, was in the game. And when I saw that structure come out from the protein crystallographers of the di-iron hydrogenase active site, I said, oh, we all know what that compound is. Let's go in the lab and make it really fast because Tom's going to be there soon. And it was, boy, was I right on that. So Tom Rauchfuss, Chris Pickett, and myself all published the first models of that system simultaneously within the same year. That opened sort of a floodgate of models for the di-iron hydrogenase active site, the hydrogen producers. And then I wanted to look more deeply at what the enzyme active site was. And what nature has done is, and has always done with these metalloenzyme active sites, is to use the protein superstructure to change our ground state structures that we can make in the laboratory. But all of the protein superstructure can twist and distort coordination sites to make the redox potentials and make the reactivity just slightly different, just different enough so that they can do reversible catalysis as is prominent in enzymes. So we wanted to go from this butterfly shape to an inverted butterfly shape in the di-iron dithiolate. And how to do that? Well, I had two wonderful students who were actually competing with each other at the time. And Tianbiao Liu was the first one to put together the abiological ligands to enforce this structure. And Mike Singleton later did this. And I should mention these students are, of course, our greatest accomplishments.
That's right. That's right. I was going to ask about something a little different, rather most important or proudest, which is the sort of, quote, eureka moment, you know, when you know, something is wow. I mean, for me, it was as simple as finding out that a phenyl ring really does have 6 carbons and it's flat, and that came out of a crystal structure. But you had mentioned the infrared spectrum and the matching of that. How about you, Don, in terms of special moments?
The earliest one was this correlation between CO force constants and charge on carbon and nucleophilic activity. I think that was that happened very soon. And in fact, we published a major paper in inorganic chemistry in the very early 70s on that issue. So that was one of the first things. In terms of other moments, I guess, you know, I'm now sort of work in the polymer community, and I was just, I was totally unaware of synthesizing polymers, et cetera. And I think learning about stereochemistry, tacticity, et cetera, that was when things really lit up, because I'd always heard lectures, et cetera, but sort of never really got into it very deeply. And until one gets into asymmetry and asymmetric catalysis, et cetera.
Do I remember right that in the early years of your research, you had somehow a big supply of C13 labeled CO that you were using for all kinds of exchange reactions that other people were not doing?
Yeah, we learned to make regioselective metal carbonyls labeled in carbon-13 CO. And in fact, I wanted to mention a paper, my inorganic publication that has the most hits is a little note that I published with a second-year undergraduate at Tulane. And that was making metal dye-substituted metal carbonyls with amines that were fairly labile so that you could make, and they started out in the cis configuration, but you could make mixed phosphine amines that were cis or trans, and then you could dissociate that second one and replace it with a carbon-13 CO stereoselectively or regioselectively. And that paper has got nearly 300 hits over the years. But it was a simple idea. But in any case, then being able to make stereoselective metal carbonyls, we could do substitution reactions. We had infrared spectrometers. Later, carbon-13 NMRs were readily available. So we were well established. We were poised because we could make the materials and had an interest in mechanisms so that we could actually study their reactivities and look at rearrangements, et cetera.
It's great that you did that also with an undergrad initially.
Yeah. Well, at Tulane, we had very few graduate students. I think over the 10 years I was there, I produced 3 PhDs, and one of those 3 finished up at A&M. So there were mostly undergraduates, but they were super students.
Well, there's a good message too for people who are interested in research and in teaching, that you can do a lot.
You can do a heck of a lot if you're involved. The students are very enthusiastic. They're bright. They know no limits. They're not inhibited like we are. So it's a super opportunity.
Yeah. And you mentioned advice to couples, but maybe this has to do with advice to research groups, and that is marshal your forces. You know, you can use undergraduates, the undergraduate synthesis lab. There's all kinds of work that you can get done with your students by sort of directing them in ways to do reviews of the literature, as well as to make starting materials in the laboratory. That's easy.
Now you've once you got to A&M, you both have substantial groups, and that's continued on over the years. What advice would you have for young scientists today in terms of how to think about running a research group and you know, getting started in that manner, besides marshaling your forces, or in addition to?
I think probably one of the biggest advice, and things are so different than when we started. You know, one goes into a position now with a lot of startup money, and so the opportunities are somewhat different. But in any case, I think the biggest mistake a junior person can make at most institutions is to assume that if you just send the graduate students in the lab, something's going to happen. I think in the early days, you have to be very involved with the lab setup, with helping students, with being a good model for them in hard work, passion for the research, treating it so that they take on the pride and make the work part of their efforts.
Ownership.
Also, they should start thinking then in terms of careers as opposed to jobs. I think students sometimes think of chemistry as a job, and I think a real chemist think of it as a career. So so there's a lot you can do to encourage students to be passionate and to work hard, etc. And also, I think it's good to think of them as colleagues more than workers, because that really establishes them then as scientists themselves, and treat them with a great deal of respect. Expect a lot of them, but treat them with a great deal of respect as well.
Yeah, it's a real challenge and talent to be able to stimulate the word that you used, Marcetta, was ownership, student ownership of a research project and how they become colleagues rather than just students. And this is very important.
You know, sometimes we say we aren't trained to manage a group. We aren't trained to be managers. We're trained to be scientists. But I think being trained as scientists is the best way, because each of those students are different, and or postdoctorals or whoever we're working with. And so we do have to look at the project, look at our overall goal, and make sure the student understands what their part is in achieving this. Of course, we're always working in this, you scratch my back, I'll scratch yours. They work hard for us. They help us with our passions, our dreams, our ideas, getting our next grant, and we help them at the base of their career. Of course, we help them later on too, because we're always in contact with the students.
What would you advise students today with regard to how they communicate their